Organic Chemistry, Chem 212, Exam 3 material, Part 2, Alkene Reactions and Synthesis. Alkenes are very reactive. There's a bunch of reactions that it can undergo. Alkenes react with many electrophiles to give useful products by addition, often through special reagents. With an alkene, we can make alcohols by adding H and OH across the double bond. We can convert an alkene to an alkyne. We can convert an alkene to an alkane by adding H and H across the double bond. We can make halohydrins by adding OH and X across a double bond. We can form 1,2 dihalides by adding halogen and halogen, XX across the double bond. Halides are formed by adding HX across the double bond. 1,2 diols by adding OH and OH across the double bond. We can even make a cyclopropane by adding this methylene group here with the lone pairs across the double bond. And we can also form carbonyl compounds. On the right-hand side here, this is an illustration in your textbook, and I just really like it when they use this flask-looking thing. Here's our alkene, again showing us the same reactions I have written on the other side. This doesn't show us the specifics. That's what's going to follow in the next slides. 2 reactions that alkenes undergo. They can undergo an addition reaction, or they can undergo an elimination reaction. So we're going to go ahead and take a preview at some elimination reactions before we get to the addition reactions. Alkenes are commonly made by the elimination of HX from an alkyl halide. This is known as dehydrohalogenation. This uses potassium hydroxide in ethanol. In this case, I'm not putting the R groups in here. You can go ahead and this is where the action's happening, but whatever is written here, be sure to rewrite here. What is important for this reaction is that wherever you have your halogen, that the direct next door neighbor carbon has an available hydrogen for this reaction to happen. We end up forming an alkene through an elimination reaction with some minor secondary products of KBr and water. Here's an example reaction, and typically in a reaction we won't show you all these hydrogens. We're doing this for illustrative purposes. This is the carbon that has the halogen on it. We need to make sure that the next door carbon has an available hydrogen, and this one does. And so we have potassium hydroxide. This is ethanol written out, CH3, CH2OH. You can either write out the chemical formula for it or write the word ethanol. And we're going to cause an elimination reaction. We have a carbon-carbon double bond where the bromide was and where that hydrogen is that left. Alkenes are commonly made by the elimination of H and OH from an alcohol. This is known as a dehydration reaction. This requires strong acids, typically sulfuric acid, and a temperature of 50 degrees Celsius. Here we have our carbon-carbon single bond. We have an alcohol, an OH on this carbon. Now again, as we saw in the previous one, for the elimination to happen, the next door carbon must have an available hydrogen in order for this reaction to happen. H3O plus is telling us we have an acid, the delta means temperature, we have our elimination, and we have water as a minor secondary product. That's why this is known as a dehydration reaction, because we lose water. In this example, this is the carbon that has the alcohol on it, so we could go either left or right. In our graphic here, they're showing us coming down here clockwise. Does this carbon here have an available hydrogen? It does. In fact, it has 2 available hydrogens, but in the line structure we don't draw them in. So what's going to happen is we have sulfuric acid, water, THF, and 50 degrees. The reagents I'd like you to learn for this class is this full set of reagents here. Sulfuric acid, water, THF, which is tetrahydrofuran, that's actually an ether, and 50 degrees. Make sure you learn this combined set. Up here is just a generic piece. This is the whole piece I want you to know. Alright, so our carbon-carbon double bond is going to form where the OH was and this hydrogen, and we can see here that the bond was formed there, and it's a dehydration, so we lose water. So that's it on the elimination reactions. This is just a preview of some of them. We're now going to move on to looking at addition reactions and then come back to some elimination reactions in more detail later. Addition of halogens to alkenes. Bromine and chlorine add to alkenes to give a 1,2 dihalide. In industry, it's a very important process. Now, Fluoride, F2, is too reactive, so it's uncontrollable, so we can't count on how many fluorides are going to go on the molecule itself. And iodine doesn't add. It needs more help, or it's too slow. So the reaction we're looking at now, specifically with the CH2Cl2 as the solvent here, is only when we have chloride or bromide. What's going to happen is both the halogens are going to add across the double bond. And because they're the same as each other, Markovnikov rule does not come into play for this reaction. That's why we're not going to mention it. But what does come into play here is something interesting. We have what's known as anti-addition. Now, what that means is as soon as one of the halogen attaches on one side of the double bond, the other halogen has to do a backside attack and come from the other side, and that's known as an anti-addition. When you have a carbon-carbon double bond in a straight chain, you really wouldn't notice that that's happening because once it's all added together on there, you have free rotation around a single bond, so it doesn't really matter. But if this reaction happens on a ring where you have a cycloalkene and it adds across the double bond, you're going to have a situation where the halogens are going to be trans to each other. This is known as anti-stereochemistry and an anti-reaction in which two ends of a double bond are attacked from different sides. The addition of Br2 to cyclopentene proves that it's anti-addition. The addition is exclusively trans. Here's the mechanism explaining why. When the pi electrons attack this bromine, it's going to be bonded actually to both of them at the same time. Take a look at this intermediate. Bromide here, it's a positive charge here, it's going to be attached to both this carbon and this carbon at the exact same time. What this means is it's shielding the bottom side from the second bromine getting in there. The second bromine just has no room, so the second bromine has to come from the opposite side, a top side attack. What happens is as soon as this bromine comes in from the top, it's going to be too many bonds to this carbon, so this bromide will let go of its attachment here and it'll swing back to this side, causing the BRs to be trans to each other. Now, technically, it's the hydrogens that we used relative to each other to call it cis or trans, but we're talking about the fact that you get a trans product. On this slide, I have some reactions on what we've already discussed, so go ahead and complete the following reactions, pause the video, come back and see how you did. For letter A, we have the starts of an elimination reaction. In fact, it's a dehydration. It's these two carbons here. They're going to cause the carbon-carbon double bond, and this will be our loss of water. The carbon-carbon double bond is going to form here because this carbon does have an available hydrogen. So we have an alkene formed with water, dehydration. In letter B, this is the set of reagents that have us make a carbon-carbon double bond where this bromine gets out of here. So it's these two carbons here involved in the carbon-carbon double bond. This bromide gets out of there and one of these hydrogens gets out of there, and we form a carbon-carbon double bond right here. These are the same carbons. It's another elimination reaction. Did you remember KBr and water? All right, the bromination reaction of 2-methylpropene. One of these bromines is going to attack one side of the double bond, and the other one, because it's anti-addition, will attack the other side of the double bond. I like to go ahead, even though it's a straight chain, I like to go ahead and show the anti-product. That way I don't forget it. If it happens to be on a ring, I make sure that I still remember it. Halohydrin formation. This is formally the addition of OH and X to an alkene with Br plus as the electrophile. This will give us a 1,2-dihalo alcohol called a halohydrin. The actual reagent is a dihalogen in water in an organic solvent. Note that Markovnikov regiochemistry is observed. Br adds first to the less substituted carbon. All right, to talk about the regiochemistry here, let's just go ahead and put some R groups in here. We see that in this reaction, because it says Markovnikov's regiochemistry is observed, our halogen is going to go to, just one of them though, is going to go to this carbon, and the OH is going to go to this carbon, because bromine adds first, just like with Markovnikov's, to form the more stable carbocation. This is also an anti-addition, so we can see they're diagonal to each other. Now, again, if it's a straight chain, there's free rotation, so technically it doesn't matter, but it will matter if this reaction was on a ring. The mechanism for this reaction is on the next slide. Let's take a look at that. Mechanism of formation of a bromohydrin. Br2 forms bromium ion, then water adds and acts as a nucleophile and opens the ring. This will not happen to aromatic rings. For this mechanism, we have the pi electrons attacking the bromide. The pair of electrons that were holding the two R's together are going to go to the 1, making the bromide ion. And we have the bromium ion. Similar to what we saw before, it's the Brs adding across the double bond, so it's holding on to both carbons at the same time. As soon as the water comes in, and whichever carbon it decides to attack, what's going to happen is then the bromide's going to let go of that bond and go to the other side. This is where the anti piece comes in. But we're not finished here. What happened is this was water coming in, a full molecule of water. That gives us this O charge here having a +1 charge. Oxygen does not like having a plus charge. It's an electronegative element, definitely does not want a positive charge. A second water molecule is going to come in and grab this hydrogen. The pair of electrons that was holding this H and OH together is going to go to this oxygen here, and now we'll have the hydronium ion being formed, and our OH is now added across the double bond in an anti-conformation. An alternative to bromine, N-bromosuccinimide, produces bromine in organic solvents and is a safer source than the previous reaction. What's going to happen is Markovnikov rule is going to be followed, where bromine is going to go to the side with more hydrogens and the OH to the side that's left over. When you write this reaction, don't forget this other stuff that has to be included in this reaction and has a lot more reagents involved. Adding water to alkenes. Oxymercuration. Hydration of an alkene is the addition of H and OH to give an alcohol. Acid catalysts are used at high temperature in the industrial process. Here we have ethylene converted to ethanol. Now the regiochemistry corresponds to Markovnikov's addition. Hydrogen will go to the side with more hydrogens and OH to the other side. With this reaction of ethylene, this again is the industrial process here, we have ethylene and water. It's an unsubstituted alkene, so you really wouldn't notice what side the hydrogen went to. We have H3PO4 catalyst, 250 degrees, and the addition reaction causes H and OH to go across the double bond, forming an alcohol. For the laboratory scale, the hydration of alkene, we would use more reagents. We use mercuric acetate in THF, followed by sodium borohydride. This is Markovnikov's orientation via a merconium ion. This set of reagents here, this is a two-step reaction, so here's the first step, number 1. This is the second step, so with the reaction arrow, you would write the number 1 with this set of reagents. That means you could actually stop the reaction at that point, and you could either react it further or not, but this is a second reaction that's happening. What's going to happen is we're going to have hydrogen go to the side with more hydrogens, and the OH is going to go to the side here. This is, again, following Markovnikov's rule. Complete the following reactions. So on this slide, I have some of the reactions we've covered, and I want you to go ahead and complete the reactions, pause the video, come back, and see how you did. All right, for letter A, this is the set of reagents you need to recognize that causes OH and Br to add across the double bond, and Br will go to the side with more hydrogens. So your Br would be here, and your OH would be here where the CH3 group was. For letter B, this is a reaction that adds water across the double bond H and OH. It does follow Markovnikov's rule, so hydrogen will be on this carbon here, while OH will be on this carbon here. For this last reaction, this also adds water across the double bond, so to be these two carbons here involved in it, and hydrogen's going to go the side with more hydrogens, the OH is going to go here. We're going to be using H3PO4 catalyst. This is supposed to be 250 degrees C, and I've noticed sometimes when I go from my PC to my Mac, I get this infinity sign instead of the degree sign. So be sure to change this. If it's in your notes wrong, be sure to change this to a degree sign, degree C. Well, how'd you do on these reactions? Be sure to practice them. Addition of water to alkenes, hydroboration. Borane, BH3, is electron deficient and is a Lewis acid. Borane adds to an alkene to give an organoborane. Boron attaches to the less highly substituted carbon for steric reasons. This is borane. Here's our carbon-carbon double bond. And what will happen is BH2 will add to one side and hydrogen to the other. Now the overall reaction happens in two steps. So this, what I have number 1, BH3THF, this is just the first step. That's what's happening up here. What's also going to happen is we need to use hydrogen peroxide, H2O2, and also a base, OH-. And what's going to happen is when the whole overall reaction happens, the OH is going to replace wherever the boron was. And this is how we add water. We have H and OH, but it goes through this step of using the borane. This is a syn addition, meaning that they add to the same side of the double bond, but it's anti-Markovnikov, and hydrogen is going to go to the side that has less hydrogens on it. Remember that boron attaches to the less highly substituted carbon for steric reasons, and then it becomes substituted with the OH. So it is anti-Markovnikov in the end. Let's look at the next slide to see another example of what's really going on. The regiochemistry is opposite to Markovnikov's rule when we look at hydration via hydroboration. OH is added to the carbon with the most hydrogens, and that's because the boron adds first and it needs more room. Let's take a look here. We have our CH carbon-carbon double bond here. The boron's going to go to this side here. After the BH3 is on here, the next reaction is bringing in the hydrogen peroxide and the OH, and it's going to go on the same side, so this is going to be syn addition. When they went on opposite side, that was known as anti-addition. When they go on the same side, that's known as syn addition. This is a nice way also to see the two-step reaction where you have a number 1 over the arrow and number 2. This is the first set of reagents that was number 1 over the top of the arrow. This is the second set of reagents that was underneath the arrow with the number 2. Here we have a reaction where we're going to make cyclopropane using a carbene. An alkene can be reacted with a carbene. This is a new group here that you haven't seen before, carbene. It is also known as half of an alkene. This is a functional group you want to add to your list of functional groups. Carbenes are electrically neutral with 6 electrons in the outer shell. They symmetrically add across the double bond to form cyclopropanes. This reaction happens in a single step without an intermediate. So these pair of electrons, they just basically land right up on here, and you're now going to form a cyclopropane from a carbene and an alkene. Let's check the next slide and see how this carbene really is in there, because you're not really going to see the carbene. Let's take a look on the next slide. You can have a CH3Cl3. The double bond here is going to be attacked by the CHCl3. When it is in KOH, it's going to form the carbene, and it's going to land right on top of here. And this, because it had 2 chlorines on it, will have 2 chlorines up here. One of the simplest methods for generating a substituted carbene is with the treatment of chloroform in a strong base. The addition is stereospecific. If you start with a cis alkene, you get a cis disubstituted cyclopropane. If you start with a trans alkene, you get a trans substituted product. Here is an example of showing the same reaction, but now showing the geometry where you have cis and trans. My starting reactant here is cis, therefore your product will also be cis. Simmons-Smith reaction. The best method for preparing non-halogenated cyclopropanes. This is the equivalent of the addition of a CH2. The reaction diiodomethane with copper zinc alloy produces a carbenoid species. When we have the CH with 2 iodines, those are pretty large groups, they make great leaving groups. This is going to be a zinc copper alloy in ether. This CH2 group is going to add across the double bond. This way we won't have to have this carbon that was added across the double bond have any halogens on it. This way we could have just hydrogens there. An example reaction on a ring would be the carbon-carbon double bond. We will make a cyclopropene on the ring itself. We're forming cyclopropanes by cycloaddition. Reduction of alkenes. This is the hydrogenation reaction. We can add 2 hydrogens across the carbon-carbon double bond. In this case, we're going to be using the catalyst platinum, palladium, or nickel. What happens is H and H adds across the carbon-carbon double bond. This is a reduction reaction. It's the equivalent of H2. It requires platinum, palladium, or nickel as powders. Gives us a much bigger surface area. You're going to see on the next slide the mechanism that this reaction literally happens on the surface of the metal. Hydrogen is first absorbed on the catalyst, the metal itself. The reaction is heterogeneous. It's not in solution. The mechanism of the catalytic hydrogenation, this is the surface of the metal that's in there, either platinum, palladium, or nickel. And what's going to happen is hydrogen is going to adsorb on the catalyst surface. The electrons, the pi electrons, are going to be attracted to the metal. And then what's going to happen is one of these carbons is going to grab the hydrogen that's next to it. And now it no longer has a carbon-carbon double bond. This carbon doesn't have enough bonds attached to it. Now, on the paper, this hydrogen's pretty far away, but don't forget that it's actually, there's a whole bunch of hydrogens absorbed on there. So there's a hydrogen pretty close to it. So we can go ahead and grab that hydrogen and it'll leave, and now it's hydrogenated in, and it is an alkane product. This is a reduction reaction because we have more bonds from carbon to hydrogen than we had before. One thing I want you to notice about this mechanism is a couple of things. One is all these reaction steps are reversible, so it's just as likely to go in the forward direction as the reverse direction. The next thing I want you to notice is it is syn addition, that they do add to the same side of the carbon-carbon double bond. So if it's on a ring, then you would get a cis product out of this. On this slide, I want you to go ahead and complete the following reactions. Pause the video, come on back, and check your work. All right, for this first one here, we need to recognize that this is the set of reagents that causes H and OH to add across the double bond, but it adds across the double bond anti-Markovnikov. On letter B, we need to recognize that this is the trans structure of a line structure. So we have to realize that our product will be trans. This is the set of reagent that causes a cyclopropane to be formed with 2 halogens on there. 2 of them came from here. A trans reactant will give us a trans product. In this hydrogenation reaction of 2-methylpropene using hydrogen catalyst, platinum, palladium, or nickel, and remember this is that heterogeneous one where we literally have the solid metal in there, hydrogen is going to add to both sides of the double bond, forming an alkane. Hydroxylation and cleavage reaction. We're going to look at the hydroxylation reaction first. Hydroxylation adds OH to each end of the carbon-carbon double bond. It's catalyzed by osmium tetroxide. The stereochemistry of this addition reaction is syn. The product that is formed is a 1,2-dialcohol, also known as a diol, also known as a glycol. These would be terms that you would be responsible to know. An alkene, the first set of conditions is when we're going to get the osmium tetroxide, and we can see down here in the breaking down of this reaction that the osmium tetroxide is in pyridine solvent. The osmium is a pretty cool molecule here. The oxygen itself on the four oxygens, the one that has only a single bond is going to bond to this carbon here across the double bond and across the double bond here. So it's syn addition. It's coming on the same side of the carbon-carbon double bond in this case, or the ring too, if we see this on a ring structure. This intermediate is then going to be removed when we bring in our sodium bisulfite and water. And these oxygens from the osmium are going to remain, but then we're going to have this hydrogen come in and make each of these an alcohol. This cyclic osmate intermediate is also something you need to make sure that you know how to draw. In fact, this whole reaction would be something good for you to have. This is, the top one is the reaction that happens. Down here shows us the intermediate that comes into play, describing it just in a little more detail. This bottom reaction is not a mechanism because we're not seeing curved arrows and stuff like that. This is just happens to be an expanded reaction showing how the intermediate is involved. So now we're going to look at another oxidation reaction. In this case, this is a cleavage reaction with ozone. Ozone, O3, reacts to alkenes, and what's going to happen is it's basically going to break that double bond in two. So going across the top here is the actual reaction that happens, kind of like I showed you on the previous slide, but if we go down we can see what's happening with the intermediate as we come around, and then we get this product. So this would be more detail. Again, this is not a mechanism, it's just showing us more detail as we come across. Well, the basic thing that happens is the carbon-carbon double bond is just cut in half right here. That's why it's called the cleavage reaction, because it just breaks this right in half. And the carbon that's bonded here will become double bonded to an oxygen, and this one will also become double bonded to an oxygen. These all come from the O3 that's in there, our ozone. So what's going to actually happen? This is a two-step reaction. You can see the conditions. We also have CH2Cl2, and this one we have in the second step, our zinc. We're also going to have acetic acid and some water. So let's take a look here. Ozone comes in and adds across the double bond, kind of like we saw with the osmium. And then we're going to get a rearrangement happening. Zinc and water are going to come in with that acid and break it up into two separate carbonyl groups. We can break these down into either ketones and or aldehydes based on our starting material. Did we have R groups here or hydrogens here on all four of these spots? One of the things we can do with this reaction is we can determine the structure of an unknown alkene. We can go ahead and take the alkene, undergo an ozonolysis, and see what products we get. So cleavage products reveal the alkene structure. In this reaction here, instead of me having you write the products, I'm asking you to write the reactant. So what is the structure of the alkene reactant from these two products? This part here, these two are going to come together. Remember, there's a carbon here. This carbon is going to bond to this carbon. Counting your carbons, we have 5 in a ring here. 6, 7, 8. 5 in a ring, 6, 7, 8. Make sure you don't lose or gain carbons in this reaction. Permanganate oxidation of alkenes. Oxidizing agents other than ozone can also cleave alkenes. Potassium permanganate, KMnO4, can produce carboxylic acids and carbon dioxide if H's are present on a terminal alkene. We can see, I went ahead and colorized this. I have this carbon in blue and this carbon in red. Potassium permanganate is going to go ahead and take one of these carbons, and one of these carbons is going to form our carboxylic acid here, while the other one here is going to break down in more steps than we can see here. Don't forget there's oxygens here, and form our CO2. This again is when we have a terminal carbon-carbon double bond. Here is an example of a terminal carbon-carbon double bond. This came from your textbook. Notice the action is only happening here. The carbon-carbon double bond's right here. We're going to break it right here. This side here is going to become our carboxylic acid, and this part here is going to become our CO2. So the reaction above is when you have a terminal carbon-carbon double bond. What do you think happens if it's not a terminal alkene? What if it's internal? What you get are two carboxylic acids. Bonus slide. So this may or may not be in your lecture notes. If not, go ahead and grab a piece of paper and write this out. Otherwise, if it's in your lecture notes, great. That means I've added it already. What I wanted to do is the different reactions we've discussed so far. I wanted to go ahead and have the same starting material. In this case, I have a 2-butene. In fact, technically, it is a trans 2-butene. And we're going to go ahead and we've got this reaction happening with NBS and this DMSO and all this other stuff. What product would you get? Same reactant undergoing ozonolysis, and this reaction undergoing the potassium permanganate reaction. Go ahead and write out the 3 products that are possible and come back and check your work. With NBS, we added Br and OH across the double bond. With ozonolysis, we broke this in half and made either aldehydes or ketones depending on what we had on the other side. But this is another cleavage reaction, and instead of making aldehydes and ketones, this one makes carboxylic acids. So this is a nice slide to compare these different reactions. In fact, what happens a lot with OChem is we know we have an organic reactant, but it's the set of reagents here that give us totally different products. What you need to start getting used to is concentrating on organic reactions on this middle piece here. What is it reacting with? What are the conditions? Notice again we get totally different products. Cleavage of 1,2-diols. The reaction of a 1,2-diol with periodic acid cleaves the diol into 2 carbonyl compounds. In this case, we have a cleavage reaction that doesn't involve a carbon-carbon double bond. This is specifically when we have 2 OHs, and we do have a breaking right here. We cut it right here, and we make 2 carbonyl compounds. So here I show you a sequence of actually making the diol with osmonium, and then we're going to take that diol and we're going to break it into 2 carbonyl compounds. We saw this reaction earlier with osmium earlier, and what this does is it adds 2 OHs across the double bond. Now that we have our 1,2-diol, we can go ahead and cut this, and we can convert that to 2 carbonyl compounds. So this is a multiple step reaction. Using reactants we found in different areas, we're able to make the diol, and then take the diol and break it up. Problems: complete the following reactions. Again, these are some reactions that we've been covering. Go ahead and finish the reactions, pause the video, come back and see how you did. For the first reaction, we have osmium, which adds OH across the double bond. 2 of them, in fact. For this second reaction, this is ozonolysis that will form aldehydes or ketones. And we have on this side, we end up getting a ketone, and on this side, we got an aldehyde. Letter C, this is also a cleavage reaction, but because it's a terminal alkene, did you notice we also form CO2 along with our carboxylic acid? And this set of reagents, again, it cleaves our 1,2-diol into 2 different carbonyl compounds. How'd you do? I wanted to introduce you to Leah For Science on YouTube. Leah Fisher is somebody who does an excellent job of explaining organic chemistry, and she has, if I'm not mistaken, close to 200 videos on organic chemistry. This one is a summary of alkene reactions, products, and shortcuts. Now, if you're viewing this on my YouTube, where I'm actually talking to you, you won't be able to click the link and watch it. But if you were to be watching this on the instructor version, you should be able to go ahead and just click the arrow, the play button on the screen itself. Now, if that doesn't work, I do have the YouTube link at the top, so you can either cut and paste it or anything you need to do like that. So this is 18 alkene reactions in 15 minutes. It's a very good overview of products including regiochemistry, syn addition products. This covers a lot of the reactions we've already had. Now this is a summary of a lot of the alkene reactions. She also has a lot of other videos getting in more specifics and more details. I thoroughly encourage you to go to her YouTube website and take a look and check out her videos. She does a great job. Additionally, she did have posted on there, if you take a look to the bottom here, it says Struggling with Organic Chemistry. It says grab Leah's free ebook, 10 Secrets to Acing Organic Chemistry, and I have the link here. So definitely go to her website. She also, if you're planning on taking the MCATs, she also has tutorials on the MCATs, and she actually does personal tutoring. So I would highly, highly recommend going to her website and checking this out. Biological alkene addition reactions. Biological OChem takes place in aqueous medium inside cells and involves complex catalysts called enzymes. This is an example of one step of the citric acid cycle. All right, so we have our carbon-carbon double bond here. What's the before and after picture? Here's our carbon-carbon double bond. It's gone. So in this reaction, we saw that H and OH was added across the double bond. That's the organic piece of the biological process. Addition of radicals to alkenes, making polymers. A polymer is a very large molecule consisting of repeating units of simpler molecules known as monomers. This is formed in polymerization. Alkenes react with radical catalysts and undergo radical polymerization. Ethylene is polymerized to make polyethylene, for example. Ethylene would react with a radical, but there's a whole bunch of ethylenes there, so once the radicals are formed, they start branching together, making polyethylene. Here's another alkene reaction here. In this case, these are isoprene units, and what this makes is a polymer of natural rubber. Another interesting piece in here is they show that this is Z geometry. The free radical polymerization, the free radical comes in, it causes the double bond on this one to grab the carbon of this. That double bond pi electrons grabs the next one, and so on. The reactivity is induced by the formation of free radicals. So this is free radical polymerization of alkenes. Common polymers and their uses. Polyethylene is used in packaging and bottles. Polypropylene, automotive moldings, rope, carpet fibers. Polyvinyl chloride, insulation and pipes. Polystyrene, that's the styrofoam cups that we see. There's also Teflon, plexiglass, and polyacetate. What this chart shows us is the monomer name, the formula of the monomer, and then the trade name of the actual polymer that's formed. You do not have to memorize this chart. I just wanted to include this because I thought it was pretty interesting. Now the process of how radical polymerization occurs, and if I were to give you a polymer, would you be able to tell me the monomer? Or if I give you a monomer structure, would you be able to show me an example polymer? That's what I need to know. Speaking of polymers, this is the website www.compoundchem.com. This is a website that I like to look at to see some everyday applications of chemistry. So throughout the year, you're going to be seeing a few posters from this site. I recommend going to the site and checking it out. It's pretty neat. So I thought this was a nice slide to show us a little bit about polymers and different kinds of compounds that we've already seen so far. This, again, is for your interest. This is not specifically on the test, but if you learned something from it that helps you understand our material, that's much better, isn't it?